think I want that, do I? No. Go over here. Course, there we go. Okay, so frames and machines will be on there. Okay, so I'll get you one of those types of problems. I'll get you an algebra centroid, okay? And I'll get you an algebra moment of inertia. I won't do the calculus stuff because we didn't really have time to cover that in any detail. So algebra centroid, algebra moment of inertia. Okay, Sheeran moment equations. We'll see how much time we have to spend on those. That may or may not be on there. I'll clarify that at the end of the week. And then the other stuff there would be 3D vectors. So remember to go back and review that. 2D equilibrium using trig, like number 2 on the midterm. And then trusses, method of joints. Okay. So that's what will be on the final. Okay. And then I'll get you a page that has a little bit of a, some old problems and such. Okay. So frames and machines, centroids, moment of inertia for sure. The centroids and moment of inertia will be algebra based. Sheeran moment, maybe. We'll see if we get through it. And then 3D vectors, 2D equilibrium using trig, and trusses, method of joints. Okay.
Not trusses, method of sections.
Right. Right. So just method of joints. Okay.
Very impressive.
Yeah.
Good job.
Yeah, that's an engineering class. It's called How to Use a Hammer. Construction guys are clapping. You did it. Yeah. Oh, I don't know. All right. Well, here we go. So let's get into this moment of inertia stuff, shall we? So we've been going over this moment of inertia. Really what we want to do, I mean, the point of this is to be able to figure out simple shapes that are made into beams. Generally the simple shapes are rectangles. They might have circles and triangles in them. And what we want to do then is we want to be able to calculate for a composite shape made of more than one individual shape, like two rectangles in this case for that T-beam, find the moment of inertia of it about a given axis. So the way you do that is you use the transfer axis theorem. All right, so we use this transfer axis theorem. What we would do then, and this isn't on a given page, this one, I just made it up, and we went through it at the end of class last time. So what we're doing here, we're finding the moment of inertia about what I'm calling the neutral axis, which on this one just happens to run at the base of the base and top of the two rectangles. But I decided I'd use the transfer axis theorem on this because it's more general. I just wanted to demonstrate that. So what we would do here, we would take bh cubed over 12, which is the moment of inertia of a rectangle. So for this first one, we got a base of 12, height of 4. 12 times 4 cubed over 12 is the moment of inertia of that rectangle about its own centroid, okay? About this point right here, okay? But then I have to add in the transfer axis theorem part, and what that is the area of that little rectangle, or that top rectangle, the flange of the T-beam, which is 12 by 4, it's 48, times the distance from the neutral axis to the centroid of the rectangle, which is 2 quantity squared. So 12 times 4 cubed over 12 plus 48 times 2 squared is 64 plus 192. It's 256 inches to the 4. So that's the moment of inertia of the top rectangle about that lower axis, the red neutral axis. And then I can do the same thing for the web or the stem or whatever you want to call it there, that thing that extends down from the flange, part B. It's got a base of 3, height of 8, so 3 times 8 cubed over 12, plus its area, which is also 24, it's 8 by 3, times the offset distance, which is half of 8, it's 4, down to from the neutral axis to the centroid of the rectangle. Square that and multiply it by 24. Now in actuality that's a negative 4, but nobody bothers with that because when you square it you get rid of the negative anyway. So what you get for that is 512. And then you just add the two together. That's how you get the total moment of inertia. Just add up the pieces. It's 768 inches to the 4. So that number gets you some indication on how much that thing will bend when it's loaded. It gets you some indication. There's other factors you need to look at with it, but that gets you a start on it. Okay. Okay. So, we okay with that? That's the basics of it right there. Now, sometimes these things will get a bit more complicated. And when they do, I go into using a chart, you know, as I've, same sort of thing with centroids, okay? So what we want to do here is find the moment of inertia of this, this beam here about the x and y axes shown, which are at the neutral axis. So what you'll see there is you've got a rectangle with two triangular cutouts. That's probably how I would handle that. You could also handle it as a rectangle with two triangular additions if you wanted. You know, either way. You could do it either way. All right. So I sub x for a rectangle is bh cubed over 12. For a triangle, it's bh cubed over 36. So those are the moments of inertia of those shapes about their own centroids. We're going to have to use the transfer axis theorem to find the moment of inertia of the shapes about that axis I've specified, 9.08 centimeters up from the base. Okay, so to do that, we're going to have to use I bar, which is either bh cubed over 12 for a rectangle, or bh cubed over 36 for a triangle, plus AD squared. A is the area of the shape, D is the offset distance. Okay, so there you go, there's the shape. So, looks like what I did, I broke it up into positive pieces there. So what I've got are the areas of the shapes. So the area of both triangles is 1/2 base times height. So 1/2, 12 by 6 is 36. That holds for both of them. And then I found the area of the rectangle, 24 by 15. 12 and 12 gets me 24, and I got 15 given right there. And that's 360. And then realizing here that I'm going to use the transfer axis theorem, I want to find the distance from, in this case, the x-axis. We'll do that first, up to the centroids of the rectangles. So what I've got here for the one on those, from the neutral axis up to the centroid, it's 7.92. What that is I'm going to go 15 up. What I'm doing, I'm measuring from the base here. So I'm going 15 up from the base. Then I'm going to go 1/3 of 6 more. So that's 15 and 2, that's 17. But that's measured from the base. So what I'm going to do, I'm going to subtract off the 9.08. And when I do that arithmetic there, I get 7.92. So that's how far it is from that x-axis up to the centroid of the triangle there. All right? And then we could do a similar kind of calculation to get to the centroid of the rectangle. That has a total height of 15, so half of 15 is 7.5. That's where that rectangle is located. But our axis is located at 9.08. So the difference between the 7.5 up from the base for the centroid of the rectangle and the 9.08 up from the base for that neutral axis is 1.58. It's actually down, so I went ahead and made that negative, okay, because they're going down. All right, and that's how we work off the x-axis. And then for the y-axis, the centroid for the rectangle is right on the y-axis, so that'll be 0. But for the triangles, it'll be 2/3 of 12, because we're coming in from the vertex going either direction. So we're coming from there, going to right and left, and the total base there is 12, so 2/3 of that would get us 8. And that's the distance from the y-axis to the centroids of the triangle. All right. So, as I did with the centroid, I've done all the kind of thinking part here. I got all the numbers now. Now it's just a matter of plugging everything into the table and just knowing that formula to run. So we're doing all right with that. Now notice again that we will name the moment of inertia after the axis we calculated about, okay? So that's what we're doing there. So what we got there, we got I bar sub x. So that'll be 12 times 6 cubed over 36 for each of those triangles. And that'll get me 72. That's just 12 times 6 cubed over 36. That's for both of them. The rectangles are named 1 and 2. The area of both triangle, I should have said. The area of both triangles is 36. The offset distance that I calculated is 7.92. So I take 36 times 7.92, I get 2258. Add 72 to that, and I get 2330. So that's the moment of inertia of each of those triangles about the x-axis. And then I can do the same thing for the rectangle. So for the rectangle, I got a base of 24, a height of 15, cube that, divided by 12, I get 6750. The area is 360. The offset distance is negative 1.58. So 360 times a negative 1.58 quantity squared is positive 899. So remember that with moment of inertia. You don't subtract it. If there's solid material there that you're finding the moment of inertia for, you never subtract it. The only time you subtract on moment of inertia calculations is if you have a cutout, something you're removing from a bigger piece you've already calculated, okay? So that is negative 1.58, but it's squared, so the negative goes away. So it's 6750 plus 899, 7649. So we can add up the three of them and get 12,309 centimeters to the 4, and that's equal to 0.000123 meters to the 4. So that's the moment of inertia in the x direction for that beam there. Okay. Now what you do with this, we get to this in the strength of materials class. If you want to find the stress, you take the internal moment, which we're about to get to, you get the distance from the neutral axis to the edge of the beam, and you divide it by I, and that's how you find the stress. And then you compare the stress to the materials allowances, whatever the material can handle. That's way beyond this class, so we'll get to that in strengths down the line. Any questions on that? Doing all right? You want to do it for about the y-axis? Just spend 5 or 10 minutes on that. The idea is the same, it's just you've got to switch some of the numbers around. What was the base for the x is now the height. What was the height for the x is now the base for this y calculation we're doing, okay? So that's I sub y. Questions? No. So I will be h cubed over whatever. And you can use all of these things and model of how to do this one. The general way we define this stuff is the base is parallel to the axis, the height is perpendicular to the axis.
This would be 0, but this would be
Will be 0
so
plus
7.
It's going to be 17.
All right, so we doing okay with that? So the triangle's got a base of 6 now, because 6 is parallel to the y-axis. The height is perpendicular to the axis, so that's 12 cubed over 12, 288. Area is 36. Offset distance is 8 and -8. So 36 times 8 squared is 2304, plus the 288 gets you 2592. Doing all right with that? And then the base is 15, because that's parallel to the y-axis. The height is 24 cubed over 12, 17,280. Area 360, but it really doesn't matter because the offset distance is 0. So 80 squared is 0, so 17,280. Add everything up, you get 22,464.
You're divided by 36 on the IYs, right?
Yeah, thank you. Yeah, I screwed that up. So, right. Yeah. I think the answer's right.
Yeah.
Okay.
Yeah.
All right. Yeah. Okay. Okay. So that's how you would do that.
Is that -8?
Yes.
Aren't they both above the x
No,
axis?
but we're going from the y-axis this time. So left is negative, right is
Oh.
positive. That's why that one's negative. But again, it'll make a difference anyway, because it just, you can square it out anyways. Okay. All right. All right, I got one other there that kind of shows a picture of that. This one was just, I guess we got time, was intended to show how you handle a cutout. So A would be the entire rectangle, B is the cutout. So we got the rectangle 7 by 12, and it's got a 3 by 4 cutout out of it, okay? So we're gonna, and I've got a picture of that beam. It's just a channel type beam with the support at either end. So, you know, we would do this process to help us find I for the beam. That will help us design the beam. Okay, so the first thing you would do on this particular problem here is to figure out where the centroid is, because that's where the neutral axis is. So you would want to find the centroid for the entire beam. That would be step number 1. So, this is the usual deal here. I find the area of the entire object. So the entire object is 7 by 12, which is 84. The cutout is 3 by 8, which is negative. Okay. And I put signs in there for the 3 and the 8. I actually think it'd probably be better, more representative of what you're really doing here to, where am I here? Here we go. To have put the sign on the outside, that probably would have made more sense, because it's a negative area, it's a cutout. So I don't think either of those signs really belong in there as I put them in there. I think it's just negative times 3 times 8, negative 24. Okay, and what I want to do next is find where the centroids are at. So what I want to do there, see, I don't care about I sub y on this one. All I need is I sub x, okay? So I want to figure out where the centroid is. So I just want to find I sub x because I'm loading the things just straight down. That's all I'm analyzing for on this one, okay? So what I would do here is I would go ahead then and set myself up to find y bar and I sub x, okay? Because y bar is where the neutral axis is for this entire object. So I got the areas, and then I want to find the distance up from the base to the centroids. So the centroid of the cutout is half of 3, it's 1.5. The centroid of the entire rectangle, which is 7 high, is 3.5. Okay. All right. So that just gets me a lot of the information that I might need, okay? So the first thing I want to do is figure out where that neutral axis is. And to do that, I'll go ahead and find y bar. That's where the neutral axis is located. So I've got everything I need to do that. So I'll just plug everything in. So my little y bar to the entire rectangle is 3.5, and my little y bar to the cutout is 1.5. And the areas are 84 and negative 24. It is important that you carry that negative through on this one. So when I multiply that out, I get 294 minus 36, 258. And the total area with the cutout is 60. So I'll take 258 over 60 and get 4.3. That's where this y centroid is. That's where the neutral axis is at. Okay. All right, so that gets me y bar, so that's up above here. So the centroid for this thing is up right about there, and that's the neutral axis, see? Okay. So that's step number 1. And then once I've got the neutral axis, what I want to do next is figure out how far it is from that red neutral axis, that top horizontal line there, down to the centroids. So I know that the neutral axis is at 4.3. I just figured that out. And then I know the heights of the centroids, 1.5 and 3.5. So I just do a little bit of subtraction there. And I'll get negative 0.8. That's from the neutral axis down to the centroid of the whole entire rectangle. And then negative 2.8. And that's from the neutral axis down to the centroid of the cutout. And those are just found by doing straightforward subtraction there. So dB, it doesn't look like I put that in there. That would be 1.5 minus 4.3, which is negative 2.8. Okay. And then just like before, you just throw everything into the formula there. The one important thing on this is just include the negatives on the cutout. The BH cubed over 12 for the cutout will be negative because it's a cutout, as will the AD squared because the A is negative. So just completely subtract the cutout. That's the deal, okay? Are we okay with that? So for the overall rectangle, it's 12 by 7 cubed over 12, it's 343. The area is 84, the offset distance is negative 0.8. But again, when you square the negative 0.8, the negative's inside the parentheses. So that becomes a positive 53.8 when you take AD squared. Just add it to the 343, you get about 379, 397. And then you got the rectangular cutout, so that's all negative there. The BH cubed over 12 is negative. The area is negative. Even the distance is, but again, that doesn't really matter. When you square that distance, it comes out positive, but you still got the negative area. That'll make that term negative. So that's negative 188 when you take AD squared. And so negative 18 minus 188, negative 206. And then you just add them up. So that's how you could do one of these for subtraction. Find the area of the entire thing and then subtract out the cutout. We doing all right with that? Do we got any questions on that business there? So, I think I already wrote them up there, but I'd like you to do 361 and 362. You can just turn those in when you do the final. Okay. Those are just similar to these. Any questions on anything? About good to go here?
Yeah. Well, no.
Okay, so I'll copy off that test review for you tomorrow, I think. I'll get that to you. We can go over it a bit on Friday. Okay.